Okay, here we go. So we are going backwards to chapter 3, sequences and series. So chapter 2, as you may recall, so chapter 2 was on basic topological notions or concepts. And then we, instead of going into chapter 3, we went into chapter 4, which is on continuity. And then we went to chapter 5, differentiation, and now we're going backwards to here. So there was kind of a fork in the road here, and we could have taken either path, but I went this way. So now we're going back to here, and it's called numerical sequences and series. But this is actually a lie, because this chapter is not exactly about numerical sequences and series. It's more about metric sequences and series in metric spaces. Okay, so I mean, some of what we'll do in this chapter is on sequences and series of complex numbers. So for that it makes sense to say numerical, but this chapter is really about something more general, which is metric spaces. Okay, so so we start off with so the notion of a convergent sequence. So if you have So you start off with a sequence. So a sequence is just a function, right, going from n into some metric space. So xd a metric space, right? A sequence is, of course, just takes every natural number and then associates it with some point, right? So you've got your space here, right? You've got the natural numbers, right? 1, 2, 3, 4, 5. And then, the sequence, will give you some sequence of points, right? P1, P2. And normally for a sequence, you denote them by using subscripts. So you don't say P of 1, but you just say P sub 1. Okay, you're probably all familiar with that. Okay, so you have some sequence, and so we want to say what we mean when a sequence converges. Okay, so does anybody know what that means? It is for a sequence to converge. So if there exists a point P in X, so there's some point P here, and something happens, then we say the sequence converges to that point, right? It's sort of intuitive, right? You expect that the points of the sequence will get arbitrarily close to this point here, right? Both arbitrarily close and inexorably close, right? So they don't go in and then jump away, right? It's not like they go in and then jump away and then keep on getting closer and jump away and keep getting jump away, right? That sort of jumping is not allowed, right? So they have to get as close as anybody would demand. And 2, they have to do so in a way that does not include sort of leaving it. Okay. So the way we express that is with the notion of neighborhood, right? So if there exists a point P with the property that given any epsilon greater than 0. There exists an n in the natural numbers such that the distance between P sub n and P is smaller than epsilon for all n greater than n. Then we say that Pn, the sequence P sub n, converges to P. and we write Pn converges to P. That's how we write it. Okay. Or the limit of P sub n is P as n goes to infinity. Right. All these things say the same thing. Okay. And if there is no such P, we say that the sequence diverges. Right. So if there's no point that the sequence converges to, then we say it diverges. Okay. Okay. So for those of you who came in late, we're talking about sequences in series. What the first idea is that of a convergent sequence. Right. Convergent sequence. Right. What does it mean for a sequence to converge? It means that there's a point in the space with some sort of magical property that this property here, right? That given any epsilon, there's a time such that past that time, everybody is within epsilon of the point. Okay. So let's do a simple example. Okay. So if we look at, say, the sequence 1 over n equals 1 to infinity, right? Then this sequence converges to 0, right? As n goes to infinity, the sequence converges to 0, right? Right. So here's our metric space, right? Here's our metric space. It's R, right? And then at time 1, we have let's say this is 0 and this is 1, right? And let's call these guys a sub n. So this guy is a sub 1, of course, right? This guy is a sub 2, right? This guy is a sub 3. This is 1/2. A sub 3 is 1/3, and so on and so forth, right? And by any reasonable notion, these things will converge to 0. Okay. Okay. What does that mean, and how do we see that in terms of our definition? By our definition, it should be that 0 has this magic property, right? 0 has to for this to converge, 0 has to have the magic property that given any epsilon, there's a time so that past that, if your indices are past that time, then the distance between your point and the limit is smaller than epsilon. Okay, so right, for a sub n to converge to 0 means that I'll say it a little bit differently. Given any epsilon neighborhood of 0, there's a time past which all points are in that neighborhood. Okay, given any epsilon neighborhood of 0, there's a time past which all points are in that neighborhood. Okay, so the way you want to think about it is that there's a clock over here, right? 1, 2, 3. There's a ticker over here, right? And at each point in time, it puts down a dot. Okay, it puts down a dot. That's the A sequence. Okay, and for the limit to be 0 means that given an epsilon neighborhood here, given any epsilon neighborhood, you can find a time that past which everybody's inside there. So for example, if I give you an epsilon neighborhood of like 2, suppose epsilon is 2, then what time will work? What time is such that past it, all the points are inside the epsilon neighborhood? Well, any time will work, right? Right? I could take time to be 1. I could take time to be 5. Any n would work, right? So like if my epsilon is 2, then I can take basically any n will do. Right? Any n will work for an epsilon of 2. Right? Okay. If I say epsilon of 1/2, then what n will work? Take 10 seconds, write something down. Write down your answer. 5 seconds. Okay, turn to a neighbor and tell them what you wrote down. I'll plug up my ears, so don't worry, I can't hear you at all. You can say whatever you feel like. Okay, what's the answer? 2, right? Because as long as n equals 2 will do, right? Because what do we want? We want that for all times past 2, is it true that for all times past 2, everybody's within half of 0? Sure, right? If you're past 2, then your denominator is 3 or higher, right? So you're definitely within a half of 0, right? Make sense, everybody? Yeah, right? Right, if I say I'd like you to be within 1,000, suppose I want you to be within 1,000th of 0. Well, what n will work in this case? 1,000, right? 1,000 will do because anything bigger than 1,000, right? If my time is bigger than 1,000, my point is going to be smaller than 1,000th, right? And I'll be within 1,000th of 0. Okay. Right, so are you getting it, right? What does convergence mean? Convergence means you can play the epsilon n game. Whatever epsilon n you're given, you're able to find an n that works for it. Okay, so like means that one can play the epsilon n game successfully. Right. That's basically what convergence means. Okay. 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 Right. Like let me give another. Suppose I had the sequence of v sub n being 1 over n squared. Being 1 over n squared. Okay. Then if I ask for an epsilon of 1/100th, what n would work? Take 10 seconds, write something down. Okay, turn to your neighbor, say what you wrote. Okay, you're all kind of nodding. It's 10, of course, right? Yeah, right, because with this of 10, anything bigger than 10, right? If n is bigger than 10, then n squared is bigger than 100, right? Right? But then 1 over n squared is smaller than 100th, right? 1 over n squared is smaller than 100th, and so you're within, and you're positive, right? It's bigger than 0, so you know that you're within 100th of 0. Yes?
So can we only say it converges if every single subsequent point is closer to P, or is that just like a product of this example?
That's just a product of this example. You could have something that sort of rushes in and comes back a little bit, rushes in, comes back a little bit, rushes in, comes back a little bit, something like that. But it has to sort of inexorably, even though it comes back a little bit, it can't so if I had something that looked like 1 over n, but then if I had something C sub n that looks like 1 over n whenever n is not a power of 10, say, and is 1 if n is a power of 10. Okay, well, that wouldn't work, right? Because you see that that guy would be, heading in pretty much like this guy, right? One at, C sub 1, C sub 2 is a half, C sub 3 is 1/3, and so on and so forth. But once it got to C sub 10, it would jump back up to 1, right? And so, and then once it got to 100, it would jump back up to 1. Once it got to 1,000, it would jump back up to 1. And you see what the problem would be, that if I took an epsilon of something like this, right, you wouldn't be able to find an n that worked, right? Because no matter what n you chose, well, at some point there's going to be a power of 10 bigger than that, right? And then it'll jump out, and so, right, it wouldn't work for all n bigger than n. Okay. But if you sort of modified it and said that it jumps less and less, then that actually would work, right? It would just be a little bit trickier to figure out the n. Okay, yes, but it doesn't have to be inexorably like that, but in some sort of grander sense. It doesn't have to be precisely inexorable, but it has to be inexorable.
Okay.
Yeah. Yeah, it doesn't have to be decreasing, but it has to be inexorable. Okay. Okay, so a couple of comments. So one remark. Convergence depends on the metric space in two senses. One, P must be in X. Okay, so if I go back to this example, of A, and I change my metric space to just 0, 1. Okay, I change my metric space to 0, 1. This one, now the sequence doesn't converge because there's no point. There's no limit point. There's no point that it converges to, right? To be convergent, there must be a point in the space that you get close to, right? But here, our space doesn't have the 0. Right? So this sequence now no longer converges. Okay. So the point must be in the space. Okay. And then the second thing is that this is kind of esoteric. Convergence depends on the metric, right? Because you have to be getting it has to be that the points are close to P with respect to that metric, right? So you could have some sort of weird metric where, so in the Euclidean metric, Euclidean metric kind of corresponds to our normal, human senses, right? Like it's getting closer, if it gets closer in the Euclidean metric, it's literally getting closer, right? In the human sense. But there are other metrics for which, this sequence actually doesn't converge to 0. So there are other metrics used in like number theory. There's something called the p-adic metric used in number theory, where this actually does not, in no way converges to 0. Okay, so yeah, it depends on that. Okay. Okay. Okay, so any questions? Any other questions? Okay, so couple of so basic theorem implications. Convergence. So again, we have XD a metric space, P sub n a sequence in X, and so here a bunch of basic facts. First off, Pn converges to P in X is equivalent to saying that given any epsilon, the epsilon neighborhood around P contains almost all of the P sub n. Almost all means all but finitely many. Okay, that actually is a technical term. All but finitely many. Yeah. Don't let your mathematical terminology mess up your daily life terminology. So like when people say almost all, they don't necessarily mean all but finitely many. Almost everywhere, just for your amusement. When you take a course in measure theory, you'll learn that almost everywhere also has a meaning. It means everywhere except on a set that has zero length, basically. So the phenomenon occurs everywhere except on a set with zero length. You know, like a set of points, for example. Yeah. Right, like you have a function and it's continuous almost everywhere. Right, it's continuous except for, you know, like a bunch of dots. Okay, other basic properties. If Pn converges to P and Pn converges to P prime, then, as you might expect, what am I going to say? Charlotte? No? N.
P equals P prime.
Then they have to be the same point. You can't have sequence converging to two different points. Okay. Next one, if Pn converges, then P is bounded. Pn is bounded. Right. In other words, it lives inside some ball. For if you have some subset of X and you have a limit point of that subset, then you can create a sequence P sub n such that P sub n converges to that point. Okay, so any limit point in the topological sense, right, can be made into a limit of some sequence. You can find a sequence that converges to that point. Okay. Okay. Let me, yes.
I have a quick notational question.
Sure.
The difference between Pn and then Pnrn with braces around it.
Oh, yeah,
that-
I should probably put the brackets
Okay,
around.
yeah, I just wanted to be sure
Yeah.
that those weren't something.
Yeah. I guess, yeah.
Because
I'm
P
just-
sub
I'm-
n would just be like the nth term. in the
That's
sequence.
true. That's true. But when you write something like this, you actually are. It's a shorthand for as n goes to infinity. So in this case, you don't put the brackets, right?
Yeah, I was looking
But
through.
but this one, but yeah,
Okay.
absolutely should be done like that. Should be written like that. Yeah. Okay. Anybody else? Okay. Okay, let me ask you a question. What do you think? If you have a limit of a sequence, must it be a limit point of the set consisting of those points of the sequence? So here we're saying that if you have a limit point, you can make a sequence that converges to it. Right? If you have a limit point in some set, then you can make a limit. You can make a sequence that converges to it. Okay. What do you think? Does every limit of a sequence have to be a limit point? This is a trick question. Let me tell you the answer. The answer is no. Okay, you don't have to be the limit. You don't have to be the limit of a set in order to be the limit of a sequence. And the reason is you could have something really silly like p sub n equals 1 for all n. Okay, so here's your sequence 1, right? At time 1, this is p sub 1, p sub 2, p sub 3, p sub 4, blah blah blah. Right? It definitely converges to this point, right? Because it's just a constant, right? But that's not a limit point, right? That's not a limit point of the set of points, right? If you look at the set of points here, just consists of one thing, which has no limit point, right? So this is, it doesn't have to be a limit. It doesn't have to be a limit point, even though it's a limit. So being a limit of a sequence does not mean that you are a limit point of a set. You know, and now I see why sometimes in some books they distinguish between a sequence. Maybe it's a good idea for me to use this notation. So I don't know if I'll do this or not, but let me just, in this one example, use this notation. So here I mean the sequence. Here I mean the set consisting of those points. Right? Here's this denotes the sequence. You know, this is a function, right? And this thing here is the set consisting of the outputs of that function. Okay, well, let's get to it. So first off, if you have convergence, then you know that given any epsilon, then that epsilon neighborhood contains almost all of the p sub n's. Right? So let's prove that. So suppose that p sub n goes to p. Okay. And choose any epsilon. Okay. So here's p. And we choose any epsilon. Okay. And we want to show that this neighborhood contains all but finitely many of the p sub n's. Okay. Does anybody see why that's pretty straightforward? Right? What does convergence mean? Right? Convergence means given any epsilon neighborhood, there's a time past which everybody's in that epsilon neighborhood. Well, that means the guys who aren't in the neighborhood are just those finite guys before that time, right? So that's it, right? Choose any epsilon, right? Since Pn converges to P, we know there exists a time such that P sub n is within an epsilon P for all n greater than capital N, right? So past that time, everybody is inside here, right? But then, so, you know, at most, P1 through Pn are not in the epsilon neighborhood. Right, so we're done. We wanted to show that, there's at most finitely many guys not in the neighborhood, and we've shown it. Okay, so that's the forward direction. Now for the backward direction, right? Suppose for every epsilon, only finitely many p sub n are not in the epsilon neighborhood P. Okay. Whatever epsilon you choose, you know that everybody's in here except for a couple of guys. Okay. Is it true that Pn goes to P? So this is just remembering the definitions, basically. So what does it mean for Pn to go to P? It means that given every epsilon, you can find a time past which everybody's inside here. Okay. So we know that only finitely many guys are outside. Can we find a time past which everybody's inside here? There's only finitely many times for which p sub n is outside. So what kind of a time do we need to choose to ensure that everybody's inside here? I'll let you think about it for a minute. Think about it. We want to show that can find an n past which all are inside. We have that only finitely many times are outside. Right? Okay, talk to a neighbor. I'll just walk outside.
I feel like I'm thinking about it too, it just has to be true.
The greatest time entity that is outside. Sorry. No, go ahead. Like time, we have some inside.
Yeah.
But you have a finite number of PMs, so we take the P with the greatest N and then make that our. And put the N.
The greatest.
So it's like P1 and P3, then you just take 3 and everything comes to.
Okay, anybody want to say something? No? Yes? No? Anne, go ahead.
For the finitely many PNs, we take the N that's greatest and then put that to be the N that,
Yeah, that'll do.
yeah.
Right, just take the biggest one, and then as long as you're past that biggest one, everybody's inside. Make sense, right? So, okay. Suppose only finitely many p sub n are not in an epsilon. Okay, we want, so we want to show that p sub n converges to p, i.e. given an epsilon, given any epsilon, there exists a time such that if you're past that time, then p sub n is in the epsilon neighborhood. Okay. So, well, we know by assumption, only finitely many p sub n are outside n epsilon p. Right? Only finitely many. Let's say call them Pn1, Pn2, to Pnk, say. Right? So whatever they are, maybe like they're P3, P1 million, P10, P20, and P35. Okay? Let n be the max of the n sub i's. Right? So look at those guys. Take the maximum value. Right? If n is bigger than the max of those guys, well, then it's not one of them. Right? Pn is not in that set of bad guys. Let me call these guys B, the bad guys. Okay? So P sub n must lie in the epsilon neighborhood, right? Because the bad guys were the only ones that lay outside. Right. Here's our epsilon neighborhood. We know that there's only a few guys outside, P3, P10, P1000. Right? So if we take our time, our cutoff time to be 1000, then if you're bigger than that number, you're not one of these guys, and so you must be inside here. The only guys who are outside were these three. Okay. Mr. Wasted. Okay. Okay, making sense? Making sense, I hope. Okay, second one. Suppose that that you have 2 points. Maybe I'll do it up here. Okay. Suppose you've got a sequence and it converges to 2 different points, P and P prime. Okay. So maybe let's do it by contradiction. By contradiction. Suppose that you've got convergence to these 2 different points, and they're different points, right? Suppose that Pn converges to P, and it also converges to P prime, but P and P prime are different. Okay. How does that cause trouble? Anybody see how we can get a contradiction? Why does that, just intuitively, why does that not make sense at all? Right? To converge to P means you make your points as close to P as you want. To converge to P prime means you can make your points as close to P prime as you want. So how close should we choose? How close do we want to make it? What would result in a contradiction here? Anybody? Yes, Charlotte.
We just choose the smallest epsilon possible.
Smallest epsilon possible. Yeah, something like that, right? Like some sort of choose some sort of tiny epsilon, and tiny should be relative to the distance here, right? So like this wouldn't count as a tiny epsilon. Tiny must be like. It has to, when we say tiny, it has to be relative to this thing here. So like 1/3 of this, say. Right, so 1/3 of this distance. Right, so we're guaranteed that there's a time past which everybody's inside here. We're guaranteed another time past which everybody's inside here, right? So that means that, so let epsilon be the distance between P and P prime over 3. Since P sub n converges to P, there exists an n such that if you're past n, P sub n lies in the epsilon neighborhood of P. Right? But since Pn converges to P prime, there exists an n prime such that if n is bigger than n prime, Pn lies in epsilon and epsilon P prime. Right? So there's one time, there's this time n, and past it everybody lies in here. There's another time n prime, and past it everybody lies inside of here. Right? Why is that a problem? Well, right, if we're past the greater of the two, then every point has to lie simultaneously in these two neighborhoods, and that's not possible because they don't intersect. Right? So contradiction. Okay. So you would write it out like by saying, but then if n is greater than the greater of those two times, P sub n lies in the intersection, which is empty. Right? Right? Because of our choice of epsilon, these things don't intersect each other. That probably, if you were doing it as homework, that you probably want to explain that a little bit more, but I'll let you do it. That would actually require a little bit of proof. Because, you know, all we're saying is that it looks like they don't intersect, right? But that's with our Euclidean metric and our sort of human intuition. But you have to show that they don't intersect because of properties of metrics, namely the triangle inequality. I'll let you think about it. We've actually done something similar. Okay. Okay. So number 3, right? If P sub n converges, then P sub n is a bounded sequence. I'll let you try that one on your own. Okay, so that's, yeah, try to do that for homework, or just for. Try to do that yourself. Let's do the last one because we only have 5 minutes. Right, so the last one, remember, is if P is a limit point of E, then we can construct a sequence P sub n such that P sub n converges to P. Okay, so here's P, and it's a limit point of E. Okay, how do we know we can construct? Maybe I'll call these guys E sub n's, because they're going to lie. Right, the E sub n's are all elements of E. You can construct a sequence of points in E that converge to that point P. Okay, why? What does it mean to be a limit point? What does it mean to be a limit point? Somebody other than Anne? Charlotte?
Every neighborhood around the point intersects E.
Almost every.
Absolutely.
You almost you're just missing one word. You said every neighborhood around the point intersects E. Every.
What the punctured neighborhood.
Punctured neighborhood. Thank you. So every you know that every punctured neighborhood intersects E, right? Okay. So right, whatever neighborhood I take, there's somebody from E inside there, right? So how am I going to construct a sequence that converges to that P? How does that give it to me? You know that this point has this property. How would you build a sequence? How would you make a sequence? Why does that guarantee you a sequence? Caitlin, do you want to try? No? But you know that every neighborhood, every punctured neighborhood contains somebody in E. And we're trying to get, what we'd like is a sequence of points that converge there. Well, we've got one point. How do we get another point? Natalie.
We could take a smaller neighborhood.
Yeah.
And like the distance is that
Yeah.
distance between E and P.
Yeah. So like take a smaller neighborhood, right? And then we know that there's somebody from E inside there, right? Take another smaller neighborhood. You know that there's somebody from E inside there, and so on and so forth, right? So what you do is you'd say, well, okay, so here's the construction. Let epsilon n be 1 over n, and be 1, 2, 3, etc. So let's take radii of lengths 1 over n, right? Then we know that for each n, we know that there exists some E sub n that lies inside of the punctured neighborhood. Lies inside the punctured neighborhood of P and is in E. Right? We know that there's somebody in the punctured neighborhood that lies inside of E. Okay? So then E sub n converges to P. Right? Because given any epsilon, right, so right now what we have is if we take length 1, length 1/2, length 1/3, radii 1/3, radii 1/4, etc., we know that there's somebody in each one. There's somebody in E1, there's somebody in the second neighborhood, there's somebody in the third neighborhood, there's somebody in the fourth neighborhood, and so on and so forth. Okay, right? So now somebody gives you an epsilon and says, give me a time past which everybody is inside there, right? So what do? What time will work? Now somebody gives you an epsilon. Okay. Now somebody gives you an epsilon and says, give me a time past which everybody's inside the epsilon neighborhood. How do you choose your time? How do you choose your time? Suppose somebody gives you an epsilon of like 1,000th. What time would you choose? 1,000, right? So let n be chosen so that 1 over n is smaller than epsilon. Right? Just choose your time so that 1 over n, I'm sorry, 1 over capital N is smaller than epsilon, right? Because then everybody bigger than that is going to be smaller than epsilon, right? Everybody, all times past that point, right, will have a distance smaller than epsilon, right? So then if n is bigger than n, the distance of E sub n to p is smaller than 1 over n, which is smaller than 1 over capital N, which is smaller than epsilon. This is by our construction, right? We constructed the point so that the E sub n's are within 1 over n of p. And if little n is bigger than big N, then 1 over little n is smaller than 1 over big N. Right? So that this second inequality follows from this. Right? And we chose our big N so that 1 over big N is smaller than E. So this thing follows from this. So this thing is by construction, right? E sub n lies in the 1 over n epsilon, 1 over n neighborhood. Right? So this thing is by star. This thing is by this thing over here, double star. And this thing is by triple star. Okay, that's it. Sorry, I've kept you late again.